Hello everyone. So Chemistry Masters welcomes you again in yet our new video related to pericyclic reaction and specifically related to electrocyclic reactions. So here in this video we are going to discuss about the ring opening and ring closing reaction of 4n+2 pi electron system, taking the example of 1,3,5 hexatriene molecule. So this video will be giving you the insight of various concepts which are being used in ring opening and ring closing reactions. So let us see all these things. As we have said in our introduction, we are going to discuss here the ring closing and ring opening electrocyclic reaction in 4n+2 pi electron system. For that, we are going to take the example of 1,3,5 hexatriene molecule. The general reaction is like this, where one open molecule is going to get converted into a cyclized structure in presence of light or maybe in presence of heat, or you can say in thermal condition. So firstly we will be discussing about the ring closing electrocyclic reaction in 1,3,5 hexatriene molecule. Now we will see that how this conversion of acyclic molecule happens to a cyclic one. So already, as we have discussed in our earlier lecture of 1,3 butadiene, that for any molecule to get cyclized in electrocyclic condition, it is always important to know the HOMO of that acyclic molecule. If we know the symmetry present in HOMO of a particular condition in that molecule, then we can easily understand that for cyclization or for ring opening, what will be the motion of the terminal orbitals. So here we will be seeing that if you talk about the molecular orbital of 1,3,5 hexatriene molecule, there are 6 molecular orbital which are designated as psi1, psi2, psi3, psi4 antibonding orbital, psi5 antibonding orbital, and psi6 antibonding orbital. So these 6 molecular orbitals are formed in the case of 1,3,5 hexatriene molecule. Now if you talk about the HOMO and LUMO condition, here we should be knowing that in thermal condition and in photochemical condition, the HOMO and LUMO get changed. Firstly, we will be taking the example of thermal condition. In a particular orbital, there could be maximum 2 electrons, and the electrons are filled singly and then they are coupled, and the lower energy orbital will be completely filled, and then the higher energy level will be filled by the electron. So if you talk about the hexatriene molecule, there are overall 6 electrons in that. So those can be filled in this way in thermal condition. So 2 electrons will be going in psi1 orbital, 2 will be going in psi2 orbital, and remaining 2 will be going in psi3 orbital out here. So that's why the psi3 molecular orbital will be considered as HOMO in thermal condition. Now here we will see that how does the acyclic 1,3,5 hexatriene molecule will get changed into cyclic structure, that is cyclohexadiene molecule. This will be the first case when in thermal condition 1,3,5 hexatriene molecule is undergoing cyclization. As the cyclization will happen, the double bond will get shift and a new sigma bond will be formed out there. And in electrocyclic reaction, we already know in the case of cyclization, the pi bond decrease by 1 while the sigma bond increase by 1. But when you talk about the cyclization in thermal condition, for that we have to see that what is HOMO in thermal condition. So in thermal condition, as you can see here, we have shown that psi3 is the HOMO, and in this you can see that what is the symmetry. So the symmetry in this psi3 molecular orbital, as you can see here, if you imaginary cut the molecular orbital from between, you can see that on our right hand side and on our left hand side, same type of orbitals are present. That's why in this particular psi3 molecular orbital, you can say that there is presence of M symmetry. If you talk about the M symmetry, we already have discussed that in M symmetry, if you want to cyclize the molecule, it is very much important that in the product also that symmetry should be present or it should be preserved. And now we will see that how that M symmetry can be preserved in the product, as well as the another thing which we have to remember here is that whenever you are cyclizing a molecule, the same type of lobes, they should be interacting so that a bonding interaction can happen. Means if you consider this particular open chain, here we are taking only the terminal orbital which has been shown to you. So this one can be considered as plus, while the lower lobes can be considered as negative. So positive lobes, either they should be joined to each other, or negative lobe, either they should be joined to each other. So here what we are doing, we have in the product, as you can see, we have done what? We have joined the positive lobe to each other, or here we have interacted the positive lobe with each other. Now when the same type of lobes are interacting, in that case you can say that the bond will form. Now we will see that how these two same type of lobe come and interact with each other. So for that we have to rotate these two orbitals. So if I rotate this orbital towards my right hand side and this orbital towards my left hand side, in that condition I can say that these two lobes or these two same lobes can get interact. So here if you see, the interaction is somewhat like this. So here we can see that the interaction happens when the two orbitals move in opposite direction to each other, and whenever opposite direction movement is there, we know that there is disk rotation, and due to disk rotation what will happen, this particular bond will form and there will be formation of a cyclic molecule. And if you talk about the symmetry, so here in this molecule we already have said that there is symmetry. This psi3 molecule is there in which there is symmetry, and when it forms the product, here also if you cut it from here imaginary, you will see that the imaginary picture is available to us. Okay, that's why we can say that M symmetry is preserved in the product also, and that's why in thermal condition, due to disk rotation, the cyclization of the molecule take place. Now here we will see that in HNU conditions or in photochemical condition, how does the reaction take place, or how does the cyclization will happen. Now we already know that whenever any molecule is irradiated by light, the excitation take place and the electron from the outermost orbital get jumped and it reaches to the next energy level. So the outermost orbital in which there is electron is your psi3, but due to irradiation what will happen, that one electron will jump and it will reach to the next energy level, that is psi4. That's why here psi4 orbital will be our HOMO. And if you talk about the HOMO, we already have said that HOMO is one of the most important component for ring closing as well as ring opening electrocyclic reaction. So if you talk about HOMO, we have to see that what is the symmetry in this HOMO in HNU condition. So whenever you talk about the symmetry in any orbital, we have to cut the molecule between to check whether there is M symmetry or not, whether there is mirror symmetry or not. So if you see, if you go towards your right hand side, the orbitals are of different kind, and if you go toward the left hand side, the orbital arrangement is of different kind. That means the M symmetry is not present in the molecule. If M symmetry is not present in the molecule, in that case certainly there will be center of symmetry or C2 symmetry, and that we can judge. So whenever you talk about the C2 symmetry, we already know that in C2 symmetry there is presence of same orbital in opposite direction whenever we are passing through the center of the molecular orbital. So if you start from the center, if you go toward this side and to its opposite side, you will find the same orbital or same type of arrangement. If you go from this orbital and if you pass in the equal distance on the other side, you are getting the same orbital or same arrangement. That's why you can say that there is C2 symmetry. So that means if we take the HNU condition or if we take the photochemical condition, in that the HOMO will be our psi4 star that is having C2 symmetry in that. And here, as we already had said, that whenever we are showing the cyclic reaction, we are not showing all the orbitals, we are only taking the terminal orbital. And if you see this terminal orbital, now here we will see that how does the cyclization take place. And we already know that for cyclization, the same type of lobe should be interacting. So this is positive lobe, here the positive lobe is on the opposite side because there is a C2 type of symmetry, and the negative lobe are again on the opposite direction. And when you talk about the product, we already have said that interaction is important so that the two same type of lobes can get interact. Now we have to see that how these two lobes will be interacting, which are of same kind. And second thing which we have to understood here, very important, that is the symmetry, that is C2 symmetry in the product should also be conserved. That is again a very important point in electrocyclic reaction. Now if you talk about the movement or rotation of the orbitals, now if I rotate this orbital towards my right hand side, to make an interaction of this left hand side orbital with the right hand side orbital, I have to rotate it towards my right hand again, so that the two same type of lobe can interact to give you the bonding interaction to form a sigma bond. And here this happened due to the cone rotation. That means in HNU condition for 135 hexatriene molecule, the cone rotation will be helping the molecule to go to change in a cyclized form. Now the another thing which is very much important to check the symmetry. So we already have said that the symmetry, whatever is present in the reactant should be present in the product also. So if you want to check that, again here you can see that if you move from one side of the structure and if you go to the center and pass to the opposite side in equal distance, the orbital which you are getting or the structure which you are getting, if it is same, then you can say that this is C2 symmetry. So here also what you can see, if I go from this particular white lobe on my left hand side, from there if I am passing to the center and going to the next side in equal distance towards my right hand side, you will see that the same white lobe is present. And similarly here there is a red lobe, and passing through the center and reaching to the equal distance on the other side, I can again get the center of the red lobe. That's why you can say that there is C2 symmetry present. So this is how we can say that in thermal condition there will be always disk rotation, while in HNU condition there will be always cone rotation for 1, 3, 5 hexatriene molecule. Now here we will be taking some example where we will see that if there is some substitution at the terminal orbitals, then how does in the cyclized molecule these substitution are present, whether they are present in cis form or whether they are present in trans form. So if you talk about the first example where we have taken the thermal condition and two methyl group, they are present outside, or you can say on my left hand side there is E arrangement, on my right hand side again there is E arrangement, because two bulkier group are on the opposite side, then I will see that in the product what will be the geometry. So for that, in thermal condition we know that psi3 is HOMO, there is M symmetry, and we already have seen that there is always disk rotation. So means I will be rotating these two orbitals in opposite direction to each other. So when they will be rotated in opposite direction, these methyl group will also go according to that. So that's why what will happen, these two orbitals will interact with each other, and these methyl, you can see that they both are going up. That's why you can say that there will be formation of a cis product in this case. Now if you talk about the another one where both of the methyl group are facing towards same side, you can say the first double bond is having E type of arrangement, while the another one or the last one is having a G type of arrangement. In that case, how does the two substitution will be going in the product? So again, this is your thermal condition, M symmetry is present. So again, side 3 will be HOMO, M will be the symmetry, and rotation will be this, means opposite direction rotation to each other. So on right hand side and left hand side, so similarly it will go in this direction, and this methyl will go in this direction. So as you can say, after the interaction, this methyl will go up and this methyl on my left hand side will go down, so that it will be giving me a trans product. Now if we talk about the HNU condition, so in HNU condition we know that psi 4 star is HOMO, C2 is the symmetry, and cone is the rotation. So whenever this happened, in that case, for interaction of these two species, I have to rotate them in the same direction, whether towards the right side, whether towards the left side, and accordingly these two substitution will also move in the same direction like this. So this methyl will go up and this methyl will go downwards, so that I will be getting trans product here. And in this case, as two methyls are facing on the same side, one is having E type of arrangement, another one is having G type of arrangement. And again, if you talk about the movement, psi 4 star as HOMO is there in HNU condition, C2 symmetry is there, and cone rotation is present. That is, this methyl will go up and this methyl will also go up along that. And what will happen, both of the substitution, that is a methyl group, will be going on the same side. That is, here I will be getting the cis product. So here we have seen that the HOMO for ring closing system is very much important, whether you are talking about the thermal condition or whether you are talking about the photochemical condition. In both of them we have to see the symmetry, and according to that we have to rotate the terminal orbitals so that the bonding interaction can happen and sigma bond can be formed. And one more thing which is very much important, the symmetries should be always preserved. Now here we will discuss about the ring opening electrocyclic reaction, and again we will be taking the example of 1,3,5 hexatriene, which is a 4n+2 pi electron system. So in this case, this closed system will get break and it will give you open structure. And again this reaction can happen in thermal or HNU condition. So bond will be broken in a particular cyclic manner. A concentrate reaction will be there, due to which this ring opening reaction will take place. And now we will see that what happened in the case of a ring opening. So as we have discussed in case of a ring closing, that HOMO is one of the major factor. Similarly here also in case of ring opening, HOMO of the molecule, that is 1,3,5 hexatriene molecule, in thermal condition and HNU condition will be the major factor. So in this case what happened, whenever you are opening a particular molecule in thermal condition, then you have to see that what is the HOMO of the product. And similarly in HNU condition, if you are opening the molecule, in that case also we have to see that in that particular condition what is the HOMO of the open molecule. So now again, if you see here, this example is of 1,3,5 hexatriene molecule. Again there are 6 molecular orbital designated as psi 1, psi2, psi3, psi4 star, that is anti-bonding orbital, psi5 star, that is another anti-bonding orbital, and psi6 star, the last and the highest energy anti-bonding orbital. Now here we will see that in thermal condition what is HOMO. So already we have seen that according to rule the electrons are filled, and in 135 hexatriene there are 6 pi electrons. They are filled like this, and this psi3 is the HOMO in thermal condition. Whenever we are opening the molecule and converting it into 1, 3, 5 hexatriene molecule, we have to see here that what is the HOMO in thermal condition, and according to that what we have to do, we have to open these two interacted lobes in the closed system. So let us see that how it happened. So as you can see, thermal condition is there. In thermal condition the HOMO is psi3. So psi3 is your HOMO in thermal condition. That is first thing. Now you have to see that in thermal condition the HOMO has what symmetry. So here you can see that in thermal condition, on my right hand side and on my left hand side, I do have the same type of orbital present. Or you can say, if I imaginarily cut the molecular orbital from between, I can see that whatever is on my left hand side, the same type of arrangement is present on my right hand side also. That's why I can say that there is M symmetry. So what I have to do, I have to get this M symmetry by moving these two orbitals in a particular way, so that this positive lobe on my left hand side and this positive lobe on my right hand side go upwards. Now how they can go upward? So if I move it on my left hand side and this on my right hand side, what will happen? These positive lobe, both of them will be moving upwards, so that I will be getting M symmetry. That means I have to do what? I have to rotate it in disk form, or you can say disk rotation will be required. So you can see that by disk rotation I have got this open structure. And another thing which is very much important, that the reactants symmetry should be preserved in the product also. If you see, the product has got M symmetry. So whether the reactant was having M symmetry, yes, it was having M symmetry. If I cut it from between, imaginary line, if I put it here, you will see that the two sides or two opposite sides are having the same type of arrangement. That means you can say that here also there was M symmetry, which is preserved in the product also. So this is how the ring opening will be there in thermal condition. Now again we will see that in HNU condition how does the ring will open. So for that again we have to find out the HOMO in the case of photochemical conditions. So here again we will be filling the electron in the same way, but as we know that whenever you are irradiating the molecule with the light, the electron which is present in the outermost orbital, one out of that moves and go to the high energy level, so that the HOMO is psi4 star now. And if you talk about a psi4 star orbital, that is our anti-bonding orbital, it doesn't have M symmetry in it, because the left side and the right side, both of them, they are of opposite type of arrangement. And we already have said that wherever there is no M symmetry, there is presence of C2 symmetry. That means when we are going to open this closed structure in HNU conditions, we have to change it in this C2 symmetry form. Or you can say here that whenever in HNU condition the closed structure is opened, it gets changed into 1, 3, 5 hexatriene molecule which do have C2 symmetry in it. And here psi4 star is our HOMO. Now we will see that how this C2 symmetry can be achieved by opening these orbitals. Now for that we have to designate them as a plus and minus for a particular condition. So here you can see that the positive lobe is on the upper side, so you can move it on your left hand side, and you can see that in the another orbital on the another side it is having a positive lobe on the lower side. So to bring it on the lower side you have to move it like this. So if you see, overall you are also moving it on the left side. So you can say that cone rotation is required for getting C2 symmetry in HNU condition. Now the another condition which is again very much important, that is the preservation of symmetry of reactant in the product. The product is having C2 symmetry, so here we have to see that whether the reactant is having C2 symmetry or not. Yes, we all know that in sigma bonding orbital C2 as well as M symmetry both are present. You can see here also, if I start from the center of this positive lobe and passing through the center and reach to the another side of this positive lobe, then I will be getting the same structure on the opposite side in equal distance. That means here also I am having C2 symmetry. So here you can say that the preservation of symmetry also take place. Now here we will be taking the example of opening of cyclic structure which are having substitution in them, and we will see that after the opening of the structure, when the 1,3,5 hexatriene molecule is obtained, in that case what happens with these substitution, whether they go in the EE type of formation or whether they go in EG type of formation. So that will be discussed according to the conditions, that is the thermal condition and HNU condition in which the ring opening take place. So firstly we will be taking the example of thermal condition. So here in thermal condition both of the methyl group are present on the same side. That's why you can say cis type of arrangement is there. Now in thermal condition we know that Psi3 is HOMO for 1,3,5 hexatriene molecule, and M symmetry is present in the molecular orbital, and this rotation is observed. That means I have to rotate the interacted orbitals in such a way that they move in opposite direction to each other. If one is moving on this side, the another should be moving on the another side. That is, if one is moving on the left hand side, another moves on the right hand side. Along with the orbital, what will happen? The methyl group will also rotate. So as the M symmetry is there, so in the product, these two orbitals should go on the upper side as we have shown. And here the methyl, which is on my left hand side, will go towards the left hand side, and this methyl will go towards the right side, so that these two double bonds will be having EE type of formation. If you take the another example where you can see in the thermal condition trans condition is prevailing, and again HOMO is our Psi3. We all know that symmetry present in 1,3,5 hexatriene molecule when it get open will be M symmetry, and this rotation is present. So again in this the rotation will be in opposite direction. It is somewhat like this. If one moves on the left hand side, another moves on the right hand side. Along with them the methyl group will also move. As the methyl group will move along with the orbital, the methyl group here will be taking EG type of formation, somewhat like this. So these two positive lobe will go up. This methyl present on the first orbital out here will go towards my left hand side, while this methyl which is downward, it will also move towards my left hand side as the rotation is like this. So these two will be shown like this, and here it will be E type of arrangement, and here it will be G type of arrangement. Now talking about HNU conditions, as you can see trans geometry is present. Now here in HNU condition Psi4 star is our HOMO, C2 symmetry is always present, and rotation is cone. Means the two orbital will be moving in opposite direction, and in the product also C2 symmetry will be there. So these two positive lobes should be on the opposite side. Means if this positive lobe goes up, this positive lobe should be going toward downwards. So along with them, these methyl group will also move like this. So here what will happen, these two lobes which are of red color or which are positive lobe, they will go in the opposite direction, and these two methyl will go apart or far away, so that EE type of arrangement will be observed. And for the last one, in the cis condition, you can see both of the methyl are on the above side. Here in HNU condition, again cis geometry is present, Psi4 is our HOMO, C2 will be the symmetry for the reactant and the product, and cone rotation is always there. So C2 symmetry means these two same type of lobe will be going in the upper side and lower side, means in opposite direction. So if one is moving on this side, the another one will move towards the same direction. That is, if one is moving towards my left hand side, another one will also move towards my left hand side. So this will also do what? Both of the methyl group will go towards the same direction. That is, here also I will be getting EG type of arrangement. So this is G type of arrangement, this is E type of arrangement, and hence what will happen, this open change substituted structure will be obtained for this closed structure. This is how we have seen that in 4n+2 pi electron system, where we have taken the example of 135 hexatriene molecule, how we can go for a ring opening as well as ring closing electrocyclic reaction, and what important factors like HOMO, rotation of the orbitals, and symmetry are always important in these particular reactions. Hope this video has cleared many of the concepts of yours. If there will be any question from your side, or if there is any suggestion for chemistry masters, certainly you can put them in front of us so that we can be helping you, or we will be getting some ideas from you and making our videos more interactive and more knowledgeable for you. Thank you for watching our video. Do like it, share our videos, and subscribe our channel.